Good afternoon. My name is Hunter Manning, and this is my submission for Lab 3 of Physics 2212 at Georgia Tech. And today we will be discussing circuits. The overall purpose of this experiment was to employ the principles of energy and current conservation via the loop rule. By doing so, we may predict the behavior of circuits containing resistors. Further, we may use multimeters to measure the values of currents and potential difference. Finally, we may examine the behavior of ohmic resistors and capacitors. To briefly touch on the main results of this lab, the measured results differ from the predicted results, which were calculated using theory alone. This is possibly due to human error, which I will discuss later in the report. I will now take a moment to discuss some of the fundamental principles in this lab. First up is the loop rule. This rule states that a change in potential difference throughout a loop of a wire should theoretically equal zero. The second fundamental principle is the node rule, which relates the current in should be equal to the current out, indicating that the sum of the currents is zero. The final principle is Ohm's law, which relates voltage to the product of the current and resistance. And we can further manipulate this law to find values for current, resistance, and voltage. We can also use Ohm's law to relate to capacitors. This form of the law states that the potential difference of a capacitor is equal to its charge divided by its capacitance. Part 1 of this experiment related to measuring different values of current and voltage in a series consisting of two resistors, one at 47 ohms and one at 100 ohms. In this part of the experiment, the system can be identified as two 1.5 volt batteries totaling to 3 volts, a wire, multimeter, a 100 ohm resistor, and a 47 ohm resistor. In part 1 of this experiment, we predicted that the series circuit should measure about 0.02 amps. We found this by using the Ohm's law equation by dividing the total voltage, which was the sum of the 1.5 volt batteries totaling to 3 volts, by 147 ohms, which was found by adding the resistance of each resistor in series. This experiment, however, gave us different results. We found that the ammeter for I1 read a current of 0.77 milliamps in one direction, and when the direction was reversed, we found a current of negative 0.76 in the reverse direction. This indicates a significant deviance from the theoretical values. Further, voltage was measured using a voltmeter and was found to be 3.1 volts, which indicates a slight difference from the theoretical value. In this slide, you can see a graph indicating the potential difference of the circuit at different locations. In theory, this line should return to the x-axis at the far right, indicating a change in voltage of 0. However, this was not what was measured in lab. As you can see, the voltage experiences significant drops in magnitude as it enters and exits a resistor. At the 47 ohm resistor, we see a slight drop in voltage, followed by a constant voltage due to no resistance. Then, at the 100 ohm resistor, we see a significant drop in measured voltage. This is due to Ohm's law, as shown earlier. Because voltage is equal to the product of current and resistance, if we increase the resistance, then the voltage would decrease. Part 2 of this experiment relates to RC circuits. In this part of the experiment, we saw the battery will light up and then begin to dim until no light can be seen. At the point where no light is seen, we consider the capacitor to be charged. Removing the battery will cause the capacitor to discharge, resulting in the light bulb beginning to light up again. In this part of the experiment, the system can be identified as two 1.5 volt batteries, a 1 farad capacitor, and a light bulb. Light bulb 1 had an internal resistance of about 10 ohms. In this experiment, we found the charge time for light bulb 1 to be about 12 seconds and the discharge time to be about 10 seconds. In light bulb 2, it had an increased resistance of 20 ohms. In this part, we found an increased charge time of about 21 seconds and an increased discharge time of about 20 seconds. Moving on to the results and the conclusion of this lab, we found that the loop and node rule are not 100% supported by the lab, but they can be suggested. And this issue is mostly due to human error. Further, part 2 of the experiment allows us to conclude that RC circuits are dependent on time due to charges being collected on the capacitor. Potential sources of error include a bad multimeter, which sometimes had difficulty measuring current, incorrect measurements due to inexperience in lab, and rounding discrepancies when calculating the theoretical values. I will now touch on the assigned what-if question. What if you charge the capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. The equation above gives us an ideal case. Removing the resistor would cause the capacitor to instantly reach the battery voltage. In reality, this would not actually happen because the battery and wires do have a small amount of resistance that is not always negligible. In practice, the measured time is longer than the time predicted to charge the capacitor. That is my submission for Lab 3. Thank you so much.